So what we're gonna do today is I prepared some stuff to talk about. I didn't assign reading because I assume you will be very busy writing your final draft and then also finalizing all of the models and stuff. And yeah, so we will spend definitely less than an hour, I think, at the beginning to talk about the material that I prepared. And then we move on to like another round of presentations, Q&A. And so the stuff that I prepared, if you got the chance to take a look, is, well, we introduced differential privacy in the sense that we show you how you can add noise to summary statistics according to epsilon differential privacy definition. But we also learned earlier in the semester about what we can do if we have Bayesian models that we can use to synthesize data, right? So that's not adding noise. That's more about we're generating synthetic versions of data from the posterior predicted distributions. So these are two different approaches. And we, in this course, mentioned synthetic data first, since it's more intuitive overall based on our backgrounds, especially all of you took Bayesian statistics, and also the approach itself is more statistical in the sense that we are thinking about modeling the data and then thinking about how to generate data from there, okay? And then as you can see that differential privacy is coming from a different angle. They're trying to provide this formal privacy guarantee that you won't go above whatever the privacy budget that you set for. So this today and probably also next week is our last lecture. At the beginning, I will mention another differentially private synthetic data. But what we're trying to do for the last 2 weeks is to give you an overview and some code and some kind of background, as well as some kind of methodology justification of how can we combine the two methods together to generate and produce what we call differentially private synthetic data. Okay, so the short story, as you will see, is that we're trying to marry the two ideas, that we are relying on Bayesian models, but we're trying to make those Bayesian models differentially private. Okay, and when we say that we want to make them differentially private, is we will try to prove that the model that we propose satisfy the differential privacy definition that we talked about before, okay? However, today we're gonna provide you a new, different way to think about differential privacy from the synthetic data point of view, but overall, it's still following the general definition, okay? So I will, well, what I just said is almost like the introduction, but I will just talk through the material that I prepared, and then we will talk about a particular conjugate model, the directional multinomial, and how to make that differentially private. And then lastly, I will give you an example, again, going back to the consumer expenditure survey data, how to generate differentially private synthetic tables there. And you can see that the title of this lecture is Differentially Private Synthetic Tabular Data. So we are, as you will see, that not working on micro data yet, okay? Micro data, as we talked about in the past, and what all of you are doing for your project is individual level data, right? Respondent level data. And tabular data, they are aggregated, okay? They are, say, producing counts of certain categories of a categorical variable or cross tabulations of multiple categorical variables, okay? So they are not micro level data, but they're also not just summary statistics, right? So earlier last 2 weeks, we talked about differential privacy by adding noise to summary statistics. And now we are sort of moving towards thinking about generating synthetic data, but we first of all stop here, like pause, and then I wouldn't say take a break, but we sort of like go somewhere in between, think about how we can generate synthetic tabular data that satisfies differential privacy, okay? So the introduction and the part that we talked about in the last 2 weeks, we talked about the definitions, right? In the differential privacy framework, what is a database, what is query, output, sensitivity, privacy budget, sorry about the typo, it should be budget, and added noise, okay? So we also talked about the implications of key terms in differential privacy. Say the sensitivity, the relationship between that and the added noise is positive, and then the privacy budget is negative related to added noise, okay? And in particular, we talked about this Laplace mechanism, how to add random noise according to epsilon differential privacy guarantee, and then it's the Laplace mechanism is generating random noise from a Laplace distribution with mean 0 and scale delta f divided by epsilon, okay? And lastly, we looked at a few differential privacy properties, and we saw how to apply that to the confidential CE database. Okay, so all of this, not all of this will be relevant to what we are talking about today, but we still gonna talk about privacy budget, okay? Epsilon is always the thing that we focus on when we're dealing with differential privacy approach. And we will talk about the privacy budget in the context of generating differentially private synthetic tabular data. And that, as you will see, privacy budget plays an important role in terms of the utility that we're gonna evaluate. And as we mentioned earlier, what we're gonna talk about today is not adding noise anymore, okay? Even though differential privacy was first developed in that way, but adding noise is mostly to summary statistics, but we are curious, I guess, more about how can we utilize leverage Bayesian models that we talked about before in the synthetic data literature to produce differentially private synthetic data. So it's not adding noise anymore. It's still going to be model-based, okay? We estimate a model, and then from there, we generate synthetic data set. Although now we have to make sure that we can satisfy differential privacy, okay? So a quick recap of synthetic data, and we won't go over the details, of course, but to highlight the conjugate data, conjugate model that we're going to focus today is the differential multinomial. Okay, so many of you, I think, are using it for your project, especially if you have an unordered categorical variable that you want to model. And now let's shift that. I mean, it's definitely good for that kind of modeling. And for today, because we're focused on tabular data, where you can think of as a contingency table, that you have one categorical variable that it has I categories, capital I, okay? And then each category will receive certain counts, okay? So in the original data, you will have a vector of counts of length I. And now we're trying to recap. Well, for that kind of data, if we're not worried about differential privacy yet, a differential multinomial model will be a good model, good candidate for that. It is conjugate, okay? And also overall computation-wise, of course, because it's conjugate, everything is relatively smooth, okay? So let me just go through the model itself, and then we're gonna move on to the differential privacy part. So we're looking at count, okay? And count vector y, okay? We use boldface here, it's a vector. And let's just say there are capital I, different categories for this variable, okay? And the y itself is the count vector, okay? So the total number, we use y dot, okay? It's the sum of y, sum of each element of the vector y. So the multinomial sampling model follows this way, okay? So suppose theta is the parameter, theta is the vector of parameters for the multinomial model. Then what we do is your model is y given theta is multinomial with sum y dot, and then according to the vector probabilities of theta, okay? So this is what the basic sampling model itself. And something slightly different from what we did, or some of you are doing for your project, I believe, is that for the model that you might be fitting, the multinomial sampling model that you have, most likely this part is 1, okay? In a sense that because we're only, say if you have a, I don't know, marital status variables, let's just say it's a marital status has 5 categories, then at the individual level, we're only assigning 1 to one of the 5 categories, right? So that's why when you write your model, most likely you have something like yi, and all that because it's at the individual level, okay? However, here we are talking about the entire count vector, okay? So there's no I, there's no subscript I. This is just talking about this vector that we work with. So if you're working with, say, marital status as that variables, let's just say it has 5 categories, then if we have 100 observations that we're modeling, then the Y vector will just be a count of vector 5, length 5, okay? And then of course the sum of the counts add up to n, which is 100 in that example. So this is the setup that we're working with. We are not working with individual level data, okay? We are working with a count vector that you have the total number of records y dot as the sum of the y, and then we assume that it has 5 categories for this particular marital status variable, and then we're using the multinomial sampling model for the overall count. Okay? So keep in mind the difference, and I should say also the similarity, especially the similarity here will be about the conjugacy, okay? So you can use the conjugate prior theta. Sorry about that, here should be both base. Conjugate prior for theta is Dirichlet, and Dirichlet has a vector of parameters as well. Will have the same dimension, so we use alpha here, okay? And alpha is a vector of the same length of theta, and the conjugacy really comes into play is that when you have a Dirichlet prior for theta, and then your sampling model is multinomial, you're gonna have a Dirichlet posterior, okay? And pretty straightforward, theta given y, now is the posterior here, will be Dirichlet y plus alpha, okay? So we had, I believe, made the analogy between multinomial Dirichlet to beta binomial, right? So, so beta binomial is the binary case, as we know. And you might not be that familiar with Dirichlet if you're not working with it for your project, but for the purpose of illustrating in class now, that you can think of, again, Dirichlet as an extension, as a multivariate version. Let me see. Yeah, it's an extension of binomial, or generalization, I should say. It's a generalization of beta, sorry. Generalization of beta that instead of only having a P as the success probability of success, you're gonna have theta as a vector. Say if you have like 5 different categories, then your theta should be a vector of 5, okay? And it should be 5 different probabilities add up to 1, okay? So, so then Dirichlet is a generalization of beta in a sense that you will not only have alpha, like 1p, but a vector of alpha in this case. And if you look at the posterior structure, it is, again, sort of like the data plus the prior, okay? So alpha is the prior that we use, prior parameters for the Dirichlet for theta, and theta is the parameters of the model, alpha is the hyperparameters, right? But it is the parameter for theta itself. So if you remember back then for beta, we use, I think it's beta AB, let's just say. If it's a beta AB, we talked about A as the prior number of success, right? And B as the prior number of failures and all that. And then A plus B is the prior sample size, right? So, so you can think of the Dirichlet as something very similar, okay? Even though the result looks, I mean, the outcome in the end, equation 3, is even more straightforward in terms of, well, we're just adding the 2 vectors, one from the data, one from the prior, and then as you can see, the posterior will be an combination, right, of the prior and the data. Okay, so anyway, so the short story here is that you can use this to generate synthetic counts, okay? And this is one way to generate synthetic tabular data, okay? So in the course, in the first major, like I guess 70% of the course that we're talking about synthetic data, we always talk about it at the individual level, like micro data, okay? But synthetic data can also be used for tabular data. In this case, if I want to model counts, I can use the Dirichlet multinomial. And what we're trying to do today is how to make this synthesizer, this Differentially multinomial synthesizer, to be epsilon differential private. Okay, so differentially private. So that's the goal. And just to refresh your memory, what we did last time, or last two times, is we have this definition of differential privacy. Okay, we have a mechanism M, okay, with domain Nx. Okay? It is epsilon differentially private for all s in range M, and for all x and y with Hamming distance 1, we have to bound, right, the log of the ratio of the probability, bound that absolute value above by epsilon. Okay, so this is the generic, or I should say the original definition that we talked about before. Okay, and might not be as applicable as what we are trying to do now. So for today, what I want to mention is, well, since now we're talking about generating synthetic tabular data, we can rewrite equation 4 into what I write equation 5 here. Okay, so so bear with me. Let me just explain that, and then I will let you discuss with your members in the breakout room to make sure that we understand what we're doing over here. Let y denote the true count vector of length I, so that's the true count, okay? And x is another count vector with Hamming distance 1 from y, okay? So that is, you have counts, right? I counts, capital I counts of each of this vector. What we're saying is that x and y is only different, again, because it's Hamming distance 1. They're only different by one record, okay? So if it's count, obviously, say, let's just say, if it's x, okay, and if it's y, okay, and let's just say it has 4 categories, okay, for each of them, okay. So, so one thing, of course, is the sum of xi and the sum of y should add up to the same, because we're fixing the total counts. We're just, you can think of as the synthetic data just moving around counts, but then the total doesn't change. We're trying to synthesize from there, okay, and when you consider x and y with Hamming distance 1, what we're saying is that the two vectors, the two count vectors, is only differed by one record, meaning that, well, maybe it's these two cells, okay, that say in x is there, I don't know, let me just, let's just say, it's 10 and 10, let's just say, and then let's just say y, it's 11 and 9, okay. So again, because it's count, okay, so it only, so when x and y are different by one record, in the output, x and y, the only difference will only occur in 2 cells, okay, because it's going to be one cell at 1 and the other cell -1, because we're just moving one record from one category to another, okay. So you can see that for any, regardless of the length of x and y, we generically use I. But in the example, we use 4, but then however, how long the length I will be for the two, what's going to affect when you have x and y having Hamming distance 1 is only going to be a pair of cells, okay? And I'm giving the example of the middle 2 for x and y. And I'm giving the example of 10, 10, and 11, 9, but it could be anything, okay? But the general story is that for count vectors, when we say that Hamming distance is 1, we're saying that one cell is bumped up by 1, right? And the another cell will be bumped down, will be reduced by 1, okay? So the main difference between, the only difference I should say between x and y is only going to appear in a pair of cells in this case, okay? So, so this is how we're defining x and y, okay? And this, by now, x and y are not very different from what we talked about before. But of course, the dimension and also the definition of x and y is different, okay? But we're still talking about Hamming distance 1, and then we have this one additional assumption that the sum of the cells add up to the fixed number, because we're not changing the total sum.
I'll do like a TFT or something.
All right, okay. So here, yeah, just to recap what we just did, we had this Hamming distance 1 of the true count y, and another count vector x. Okay, we assume that they have the total sum fixed, but they're different by one record when we mean by Hamming distance 1. Okay, so what we're gonna do, okay, so sorry about that. I think this is a typo. Let me just correct this. So this, it's not y dot star, it just be y star, but it should be bold. Okay, we're saying that let y star denote an epsilon differentially private synthetic count vector. Okay, it's a vector, and it's the same as what we have before and below here. Sorry about the typo. And we use theta to denote the model parameters. Okay, so in such setting, epsilon differentially differential privacy requires, instead of what we saw earlier in the original definition, requires this. Okay, so this is, again, both of this are the synthetic, right? The synthetic count vector, and we say that they it is satisfying epsilon differential privacy because of this definition. Okay, so keep in mind that theta are the model, theta is the model parameters, and it is a vector, and then x and y are the y is the original true count, and x is another count vector with Hamming distance 1. Okay, so I want you to take the chance now to think about the definition that we put through here. Like equation 5 is just what we are working with under the differentially private synthetic tabular data framework. And what we talked about before is this one. They're not very different, as you can see. And I want you now to make the connection of why we, or how, or whether we can, and why we can use equation 5 when we're talking about a epsilon differentially private synthetic count vector, that we phrase everything in this way. Okay, so let me come back. So any quick comments? I mean, nothing important, like very important to report back. I just want to make sure that earlier we're using the original definition when we're thinking about adding noise, right, to summary statistics when we're talking about differential privacy, but now we're working with synthetic data. So we are replacing how we express the probability, right? We're re-expressing it in a sense that here we're looking at the probability, right, of getting the synthetic, differentially private synthetic y star given the parameters and the true count, right, on the top. Whereas in the bottom, we have the probability of getting the epsilon differentially private synthetic count given another count vector with Hamming distance 1 and the parameters. And we want to bound this ratio, the log of this ratio, the absolute value of the log of this ratio above by epsilon. Okay, so this is, again, if recall what we did before, that we're trying to make sure that when we have similar inputs, our outputs wouldn't be that different. Okay, so that's the key to thinking about differential privacy in the first place. And now, putting everything in the context that we're working with right now, we, instead of equation 4, we're writing equation 5. Okay, and you will see that later when we try to show you how to prove the method that we're going to propose works. We have to follow this definition of equation 5. Okay. Make sense? Quick questions, comments? Okay. All right, sounds good. If not, like I said, if we can get the Dirichlet multinomial synthesizers to satisfy equation 5, then we can produce what we call differentially private synthetic tabular data. And again, that's the title of this lecture. And now we'll see how we can make that happen.